I was saying that, so it takes memory, so we cannot do it for large state spaces. It's not tractable. So that's why people try to approximate it. It's funny because we are approximating the approximate. So we can use those kernel smoothing, the trick that we use in machine learning a lot. And one of the simplest bases, let's say, is this one. And sometimes we call it average. We call this averager. And so instead of having a lookup table, tubular thing like this lookup table, we have a rich, deep learning approach. So for any state, we have a different Q-value action. Q-value action 2, Q-value action n, and we are approximating the approximate, as I said. And the algorithms for large state spaces, the simplest one is the approximate the Q table with linear basis function. Because we don't have enough memory to do it for all states, so we approximate it. And we also update the weights, because that neural networks, you should update the weights. And so this is the approximate Q learning. We try to reduce this gap. And finally, your parameters converges. The only true wisdom is knowing that you know nothing. And finally, the third lecture, what is that? This is the policy optimization. So it is nowadays policy optimization. There are lots of articles about it. And as you see, policy-based is a different paradigm. It's different from value. Skip this model-based for a moment because it is related to nonlinear control system and the way people do it in electrical engineering. That, for example, you need the model of electrical grid or robotics or aerospace, everything. So you need your model of your engine, compressor, everything. But in value-based things and in policy, those are model free. But if you are on policy gradient, for example, when you go, it is less sample efficient in comparison to a very good model base that we do in control engineering, because we know already the dynamics. We can approximate those differential equations. You can do lots of things. But when you don't have that model, you should rely on policy gradient. So 10 million time steps in comparison to, of course, in gradient free, we have 100 million time steps. So this is the cons for policy-based approach, one of the cons. And there are, as I said, value-based approaches like SARSA and those things could be combined with policy methods to create great algorithms, such as those under the category of actor-critic. And we can combine also model and value and policy, the three major paradigms. And if you combine them, you can, for example, create some algorithms like VPN, value prediction networks. And there is a difference between on-policy versus off-policy. Of course, it's more complicated than this one. You should have, when you read lots of articles, you understand what is the difference. So in on-policy, agent can pick actions, but in off-policy, agents, they can't pick actions. So learning with exploration, playing without exploration. And of course, there is always a trade-off between exploitation and exploration. Exploitation, for example, you are going along the gradient, But in exploitation, you just randomly move to reach, because we are exploring to see if we don't miss any of these minimums, local minimums. And the policy optimization, we are very pragmatic, because you want to just pick your policy. You just want to pick this policy. This is the straight approach to this problem. And conceptually, policy optimization, we are optimize what you care about. But dynamic programming is just indirectly approaching the problem. As you have seen, you try to optimize, to converge the value function, and implicitly, suddenly you notice that you know the actions. But in policy optimization, in a straightforward manner, you go along that direction for in order to optimize what objective you really care about. And empirically, it's more versatile and more compatible with rich architectures, policy optimization. But on the other hand, dynamic programming is more sample efficient when they work and more compatible with exploration and off-policy learning. But policy optimization, forget this one is not a good sentence. So stochastic policies explore poorly in many problems. And policy gradient methods often converge to suboptimal solutions. And I understand why. Because everything depends on the initial conditions. Just like the life is non-convex, and what if you have infinite amount of local points? So episodic reinforcement learning, you have some trajectories. One trajectory, the other trajectory. When I write these sketch, suddenly I remember Feynman integrals and those past integration, because you try to see all of them. In physics, it has a lot of meanings, in Lagrangian and those things. And if you read Feynman path integrals, you will understand the importance of just enumerating all of them and integrating over all of these paths that we could possibly generate. So we want still to maximize the expected return given your policy. So among all policies, of course, the total return is total reward is the reward of all of these small steps until the final horizon. Length minus, and this is the horizon. The horizon is, if it is infinite, h could be infinite. So we assume that h is finite. So we have a finite number of states, action, rewards. And we choose the parameterized policy because we want to pragmatically solve the problem. We should approximate it with some neural networks. So that's why these parameters, billion parameters of neural network, a deep learning arises. But policy gradient method could be, it's in comparison to deep Q learning could be faster. It depends on how you implement it. And in the literature, you call this term actor critic, or in advantage actor critic it arises. So it's always, this term is fixed. So you see it everywhere. You see the gradient of log of policy everywhere, but the different names here arise, advantage or delta in TD actor. So it's good to have this in mind. And the simple relations is that forget everything. It's just calculus, okay? It's just a simple technique. We call it score function. We use it in variational inference in machine learning and everywhere. So if we just write the gradient of expected of some function, and the expectation of, so now it becomes f of x log of p of x given theta, and x is a random variable. And then this gradient, because it depends on theta, so it goes here, and you can integrate this like this. The gradient. And so until here, it's just simple math. But here, you just use what comes to your mind when you see this. Oh, it's a Monte Carlo. So that's why you approximate this with these samples, and just you sum all of them. So we take some samples from this distributions, but now you apply it for reward. So the same formula here, we apply it for a reward function. So instead of this f of x, could be any function, we call it reward of tau is trajectory. So state, action, reward, state, action, reward, state, action, reward. So different trajectories, really. The probability of the entire trajectory is probability of tau given theta. And so it's simple thing that depends on the structure, because they are independent, so you can multiply all of them. But in real things, when you will notice that you don't even need to know the transition probabilities, because when you want to prove something, you see that there are multiplication of some terms, but they will cancel with the denominator. So you don't even need to know the transition probabilities. And that is the beauty of that transition probabilities are gone. Especially here, what are we doing? We are just taking the gradient, and so it is not related to theta, so it vanishes. And we have a baseline at each step to reduce. Of course, you can learn it. We can learn anything in machine learning. You can learn baseline as well to reduce the variance of policy gradient. And it's just simple math, and this is the policy gradient method. You have advantage estimate, this return minus the baseline. Oh, by the way, there is a library called baseline 3 in PyTorch you can use, and also you can include the gem of OpenAI, and then you can run all algorithm of reinforcement learning very quickly, because it is already implemented. All of the algorithm are implemented. Even many of the models like Atari and many games are implemented. So you can modify those codes, or you can just run those codes, or different training system or different reward system. And so this is a beautiful thing in reinforcement learning. It's a huge community working on that. And I really enjoyed it, baseline 3. For example, in 5 lines of code, you can implement any algorithm for Atari or any other game that you like, especially those games that are already implemented in baseline 3, because they have their actions, they have their observations, they have their reward system. You can also modify the reward system. And this algorithm, you update the policy, because you have policy gradient estimate, and then you update it. And finally, I want to talk about trust region policy optimization. I really worked like all of the articles of Peter Abil. Of course, I think John Schulman was his PhD student, if I'm not wrong. And everybody knows Michael Jordan from statistics. And Sergey Levin, I said that you should watch his lectures in YouTube, very nice lectures. I mean, more than 60 videos about reinforcement learning, starting from very, very basic thing in robotics. Very beautiful videos. I really enjoy watching them because it is well organized. You see all reinforcement learning in these lectures. In these 50 lectures, it covers very beautifully. Of course, you should also watch the lectures of Peter Abil. I mean, his boot camp is now available in YouTube, and you can watch. It's about 11 videos of his. Of course, he only talks in 3 of the lectures, but it's very nice. Another article which is very important that I may explain in future is this high-dimensional continuous control using generalized GAE, generalized advantage estimation, with almost the same authors from Berkeley. And our algorithm, as I said, is model-free. We don't care about model-based for the moment because they use it for some things that we don't need that because we are not talking about control engineering and robotics and those things. So in model free, which is a huge topic and very live topic, we will talk about trust region policy optimization. Of course, this is proximal policy optimization. This one is also beautiful. This one is one of the most popular approaches. But today, I just concentrate on trust region policy optimization because of its theoretical understanding. So your model 3 could be either Q-learning or policy optimization. You can also combine Q-learning and policy optimization. And so let's focus on, because we have lots of policy optimization methods. For example, gradient-free is covariance matrix adaptation or cross-entropy. But what I really like is this one, trust region policy optimization, also proximal policy optimization. Of course, you should watch my proximal optimization in my playlist for optimization in my YouTube channel, where I talk about different optimization methods. One of them is proximal approach and the proximal operator. And this article uses these ideas for reinforcement learning. And so let's talk about trust region policy optimization. So, in optimization, you could, your step, because you have to choose your step in each iteration, your step size could be different, could be chosen from a different paradigm. For example, one of these paradigms is line search, but the other one is trust region. This is trust region, and so in trust region policy, of course, this is the probability. Policy is just probability because you want to know, given a state in action, what is the probability of reaching some states. So it's a mapping. For example, in this state, we should have what action with what probability. You choose what action with what probability. So it's a probability of action because it's a stochastic policy. And so we call expected discounted reward, eta of of your policy is expected discounted reward. And we have state action value. We're just reviewing it. It's just, and then value. So state action is more general than value. And the difference is called advantage function. I mean, how well your action is. If this